What is the problem with Euclidean geometry's parallel postulate? Imagine trying to build a perfect flat world where every line you draw behaves exactly as you expect. Now, what if one rule about lines and angles doesn't quite fit? That's what makes the parallel postulate so interesting. It's a rule in Euclidean geometry that says, given a line and a point not on that line, there's exactly one line through that point that never intersects the original line. Sounds simple, right? But here's the catch. It's not as straightforward as the other rules. It's long, a bit confusing, and not as obvious to understand. For centuries, mathematicians wondered if this rule could be proven from the other, simpler rules of geometry. They tried everything, but every attempt ended up assuming the rule in some way. That meant the parallel postulate might be independent of the other rules, which was a big deal. If it couldn't be proven, then it might be just an assumption we accept, not a fact that must always be true. This idea opened the door to new kinds of geometry where the parallel postulate doesn't hold. In these new systems, called non-Euclidean geometries, the rules change. In hyperbolic geometry, through a point not on a line, there are many lines that never cross the original line. In elliptic geometry, no lines are truly parallel because all lines eventually meet. These systems show us that the parallel postulate isn't an absolute truth but a choice that shapes the kind of geometry we're working with. This realization changed how we see space and shapes. It helped us understand that the rules we take for granted in flat, everyday geometry are just one way to look at the universe. When the parallel postulate is altered or removed, many familiar facts about shapes and angles also change. For example, in non-Euclidean spaces, the sum of angles in a triangle can be more or less than 180 degrees. This is useful in physics and cosmology, where space might not be perfectly flat. So, the problem with Euclid's parallel postulate is that it's less clear and more complicated than the other rules. It's not something we can prove from the rest of the rules, and whether we accept it or not leads to very different worlds of geometry. This makes it a key point in understanding how shapes, lines, and angles work in different kinds of spaces. It's a puzzle that helped us see that geometry isn't just one thing but a flexible way to describe the universe around us.